So hi, thank you for the invitation. I'm going to discuss upper atmospheric remote sensing using this really unique opportunity that we've got coming up in a month. So the region of the atmosphere that I'm going to be talking about is the ionosphere. I know we've heard some about it, but you can think about the ionosphere as sort of like the border zone between Earth and space. It's ionized by X-rays and extreme ultraviolet light from the sun, and it's an electrically charged region at the top of the atmosphere. It's split up into different layers. The region that I'm interested in is the D region, which is at the bottom. The reason this is hard to study is that it's too high to reach with hot air balloons. It's also too low to reach with satellites. There's not enough. There's too much air for a satellite. So radio waves is really our only means of studying it. For this reason, it's been called the ionosphere. So let's look at radio wave propagation. So a radio station on the ground will send a gigahertz signal that will go right through the ionosphere for the most part. Lower down, a megahertz signal where AM radio is will return back to the Earth. But these low frequency waves in kilohertz will bounce back and forth and zigzag and reach really far distances. So how do we know this? It turns out that for decades we've been observing lightning generating these low frequency waves that we can pick up from really far away. And I'm going to show you an example. On the map there's a lightning stroke in the South Indian Ocean. We've got a receiver set up in Juneau, Alaska, and that red splotch there, that's a little fingerprint of that lightning from thousands of miles away. We can pick up these signals echoing around the world multiple times. So why do we care? So the ionosphere affects radio communications for the aviation industry, for satellite signals. There's important impacts in the space environment and the Van Allen belts that affect satellite protection and astronaut safety. And there's some practical uses of VLF, including underwater communications, navigation, and there have been some suggestions of being able to predict predict earthquakes by observing low frequency waves. So we work with what we call the Earth Ionosphere waveguide, which is the system of guiding these kilohertz waves to really long distances. Now, during the daytime, when the sun's influence is really strong, you get reflections at about 70 kilometers altitude off the Earth's surface. At nighttime, though, when the sun's influence greatly diminishes, the reflection is much higher. It's more like 85 kilometers. Now, we can see this very stark transition very clearly in our data set, and I'll show you an example when the side flips. There's a radio transmitter in Maine called NAA. It's at 24 kilohertz. We have a receiver in Delaware. So that plot right there, that's 4 days of the strength of that radio signal at that receiver. And look at that daily variation, day, night. That's the rising and setting of the sun and the stark changes in the ionosphere. If you also look at the last couple days, there are those extra little blips in the daytime signal. Those are actually solar flares coming in from the sun and creating a lot of extra ionization. So we can actually pick this up. Now the eclipse is really interesting because it's the only time that we have a spot of what looks a little bit like nighttime surrounded by daytime. And so we get this unique effect where we have this sort of spot that's actually going to scatter waves in all directions, very much like a radar will scatter off of an airplane. So we're expecting to see this effect with receivers on the ground kind of surrounding where this eclipse is. Here's an overhead view. Ordinarily we just have a beacon and a receiver. We just have a straight line laser beam signal. On the day of the eclipse, we're going to have this extra path created when the signal essentially reflects off this eclipse zone and makes it to our receiver. And the receiver will essentially pick up a combination of all this. So we know that this is going to happen because we've actually seen lightning do this all the time. These sort of patch disturbances. So here's an example. These are two transmitters. The signal's picked up in Delaware. And if this video plays, you'll see the video will not play. So lightning causes a rapid disturbance in the signal strength is what you would see. So we want to learn a few things. We want to understand influences on the ionosphere, both from the sun but also from lightning. We want to understand more practically how are radio communications affected by these sort of patch disturbances in a number of ways. So here are the observations that we have set up. The blue stars are our receivers that we have deployed. The circles are transmitters that we'll be looking at. And the gray lines are all the paths that link them. And if this video plays, you'll see the eclipse spot sort of sweeping across the map. There it goes. So all those red lines that you're seeing are basically extra scattering paths that we expect uniquely on this eclipse day. And you can see from this sort of mesh grid, we should be able to do some interesting imaging of the ionosphere. That's our goal. So I'll just conclude by saying this is a really unique opportunity. We're excited about it. I want to thank my students. One of them here is Nick Gross. And thanks to the NSF for supporting us, as well as to the educational institutions that are actually hosting our equipment. Thank you.
Thank you. Any questions for Morris in the room? Oh, here we go.
Hey there. I was just wondering if you could go back to that slide with the animation and kind of re-explain what exactly is happening with those red lines.
Which,
Like,
okay.
That one, yes.
So what you'll see is, you see the orange dot sweeping across. When it gets close to an existing path, we expect that sort of secondary signal to appear. And so I sort of just in the animation make an extra red line just to show that. So a red line is basically an extra signal that's going to appear because of that scattering off of the eclipse spot. Does that make sense?
So what exactly are you like collecting from those?
We're collecting the amplitude of the radio station as a function of time. And so when two signals combine from two different locations at the same time, they can either add up constructively or destructively. So we see changes in the amplitude, which tell us that there's an extra signal added on top of the always there signal.
And how many of these locations do you have?
The receivers, we have about 10. The transmitters, there are 5 in one in this VLF band, and there's a couple dozen in a different band called NDGPS.
So what is kind of the end goal of this? Is it to kind of test your models, see how accurate they are? Or are you hoping to gain like new information about the ionosphere we haven't had before?
We want insights into the lightning impact on the ionosphere. We want insights in the sun's influence as well, and then map that to how are radio communications affected in general. So not just when an eclipse happens, but any time.
Okay, great. Thank you.
Sure. Thank you.
Thank you, Morris.
All right.
Cheers.